Chapter 17 Notes. Field lines go away from pluses, they go towards minuses. Away from a plus, towards a minus. Two plus charges, field lines are going away. I don't have an example of two minuses, but the lines look exactly the same except that the arrows are going towards the minuses instead of away. Between parallel plates, the field lines are parallel, except at the ends they get a little bent outwards. They're going straight from the plus plate to the minus plate. Now these field lines are imaginary lines. They don't exist. They're just showing the direction of a force on a positive charged object. The Earth also has gravitational field lines that would be pointing downwards. And again, these are imaginary lines showing the force of an object would be going downwards. Moving an object against these field lines takes work. On the Earth, it takes work to lift a rock. Between parallel plates, it takes work to push a positive charge from the negative side to the positive side. Work is force times distance, and for the parallel plates, we know the force on the charged particle is Q times E, where E is this field that we're moving that charged particle Q through. D would be the distance between the plates. On the Earth, the force is the weight of the object, M times G, and the distance we're lifting it is the height. Work stores energy in the object as potential energy. Both the rock has potential energy and the charged particle have potential energy after we've pushed it upwards. If we take our potential energy formula and divide both sides by m, potential energy divided by the mass is what we call potential, which is what's left over is the G times H. And what that means is this location has a potential, whether the rock is there or not. That field exists at this point and this height exists at this point, so the potential exists. All we need to do is put a mass there and suddenly we have some potential energy. This is true with the parallel plates. At a certain spot we have a potential there. Whether the charged particle is there or not, the potential is there because the field is there and the distance is there. Once we put a charge there, we have potential energy. So this is a formula for potential. V is a symbol for potential. It's defined as potential energy per charge. Moving an object with the field lines as the object moves downward takes negative work. We know that with an object that it's going to move all by itself. Same is true with here. That positive charge is going to repel from the positives on the top and attract towards the negatives on the bottom, so it's going to move down on its own. We call that negative work. The amount of the negative work is still calculated with the same formula. So how much energy does it have as it hits the bottom? We know when we're pushing it up we get potential energy, and that potential energy changes to kinetic as it comes back down. Right? It says the kinetic energy gained by the object equals the potential stored in it, which is equal to the work done pushing it against the field in the first place. So our KE, our PE, our work are all equal to Q times V. Very important concept. This will come up many times in the next couple weeks. Sample problem. You'll see this on the next test. You'll get it wrong and I'll yell at you, and then it'll be on the test after that. You'll get it wrong again and I will yell at you again. Please pay attention and take notes. How fast will the object be going when it gets through the other side? We have two parallel plates. This one has a negative charge on it, and we have an electron over by the electric charge. The electron is going to repel away from the minuses and be attracted towards the pluses. Right? So it's going to come flying through the plates. How fast is it going when it gets to the other side? This is just conservation of energy. We're starting with potential energy over on this side, Q times V, and it's changing to kinetic energy on this side, 1/2 mv squared. We put these two formulas equal to each other and solve for velocity. We need to be very careful of the way you write the letters. Small v is velocity, big V is potential. How does potential energy change as the object moves perpendicular to the field lines? This line perpendicular is called equipotential lines. Anywhere along this line has the same potential. Just as anywhere along this line you're at the same height, you have the same potential energy for that rock. So how much work is done when we're moving it perpendicular to the fields? We know that work is a dot product, force dot distance, which depends on the cosine of the angle, and it means the force and the distance need to be parallel to each other. If we have perpendicular force and distance, we have zero work being done because that cosine of the angle between them is zero. On a problem like this, when you're pushing it upwards at an angle, the moving forward part doesn't do any work, the lifting up does the work. To find what that distance moving upward is, we'd be using that cosine formula. That's what the cosine part is doing, is finding the distance between the plates. Equipotential lines are perpendicular to the field lines. Right? The field lines are going from plus to minus. The potential lines do circles around them. So sample problem, what is the potential at point P? We could do a circle around here. Anywhere along that circle has the same potential. I know these two formulas. The potential is equal to the field times the distance away from where the field is. And for a point charge, the field is kq over d squared. So I put these two formulas together. One of the d's is going to cancel out of the formula, and we're left with the potential formula for a point charge is kq over d. What is potential at point P between parallel plates? We're using this formula. The potential is the field times the distance between the plates. Notice that these formulas are different. You cannot mix them up. We can't use this formula with point charges. We cannot use this formula with parallel plates. This is a mistake a lot of you will make, and you will get yelled at. The easy way to remember is that K is only for point charges. We have the formula for forces, kqq over r squared, for point charges only. We have the formula for fields, kq over r squared, for point charges only. We have the formula for potential now, kq over r, for point charges only. All right, levitating an object. The only way to make something float is if they have like charges, and like charges repel each other. This is the only way things can repel. And this force, of course, is going to be balancing with gravity, so they cancel each other out. We could also use this to solve for maybe how many electrons are on here. We could put the mg equal to the kqq over r squared. This is very similar to Millikan's experiment. On his charged particle, we have gravity pulling down and the electric field pulling upwards. However, what's different is on my levitation, we're assuming both of these act like point charges, and we would use the point charge formula, kqq over r squared. This is different from Millikan's levitation. He was using a charged particle between parallel plates. So we cannot use the point charge formula when we're solving for this. We have to use the parallel plate formula, which the potential was E times d. All right, we talked about this several times. If you were a bird, where would the safest place be during a lightning storm? Although wood is the insulator, trees hold a lot of water, which act as conductors. And you can see, I don't know if you can see the picture very well, the lightning will go through a tree. Quite often, lightning strikes trees. The safest place to be is in a metal cage. We could be out in the middle of a field in a cage, and you would be safe. It's called a Faraday cage. Here's an animation to show how that works. Here's an electron on a metal sphere. What would happen if I add another one to it? As I move this one close, this one moves farther away. These are like charges. They're going to repel each other and stay as far away as possible. Looking at the field lines here, there's a little area in the middle where there's no field lines because these are repelling each other. If I add another electron to the sphere, all of them move, so they're all as far away as they possibly can be from each other. Looking at their field lines, this area in the middle is getting a little bit larger where there's no field. If I add a fourth electron, again they move, so they're all as far away as they can possibly be, and this area in the middle is getting even larger where there's no field because all these lines are repelling each other. Finally, when we get to a point with hundreds of electrons, there is absolutely nothing in the center. There's no field lines, which means there's no force, no electric field inside of a metal object. Here's a trick question that was on last year's AP test. We know the field is 0 and the electric force is 0. Does that mean the potential is 0 in the center? This is a trick problem. There is a potential in there because the way we find a potential is by taking a positive test charge and placing it in the center of the sphere. The positive test charge has its own field around it, and when we put it inside the sphere, that field is going to interact with the electrons and create some potential energy. As soon as I let go of that charge, it's going to take off to the side. So it has potential energy on the inside, and that means there is a potential there. It's just a matter of putting a charge there. Just like we said on the Earth, if you're holding an object up in the air, it has potential energy. That particular space has potential, and it turns to potential energy as soon as you put an object there. Same as here. We have that point has potential, and as soon as I put a charge there, then I have potential energy. And I know that as soon as I let go of that